Welcome to week 3 of the multi-step synthesis project at Tacoma Community College. As you remember, we had 3 different pathways through which we could make methyl meta nitrobenzoate. This week, we're going to look at the last step, the nitration reaction.
Okay, the first part of this reaction is to set up an Erlenmeyer flask that contains nitric acid and sulfuric acid. Before I begin, it's important to recognize that nitric acid, when it's concentrated, is quite harmful, so we need to handle it with extra care. And sulfuric acid, when it's concentrated, is also very dangerous. In this case, sulfuric acid is actually the stronger of the 2 acids and will protonate the nitric acid when added in. So in the first reaction, the nitric acid will take one of these protons from sulfuric acid, and what will happen is we will generate a new intermediate that has a really good leaving group on it. And what I mean by that is when we protonate this oxygen, it has a positive charge, and this water is now a really good leaving group. The conjugate base in this reaction at this point doesn't really do much. It's just kind of hanging out as a conjugate base, but let's draw it in so we don't forget that it's there. Okay, so in this next step, what we're going to do is we're going to kick off this leaving group in one step. So in this step, what's going to happen is we're going to form a new high energy intermediate where nitrogen has a positive charge. We're going to kick off water as our leaving group, and we'll have the conjugate base of sulfuric acid just floating around in solution. So really, in your first Erlenmeyer flask that you're making, this is exactly what we are generating in the flask. This reagent right here is the key reagent. This is called the nitrosonium ion. It is a really powerful electrophile that can react with aromatic rings. In our second Erlenmeyer flask, we've got our methyl benzoate, and this methyl benzoate is dissolved in H2SO4, sulfuric acid again, but this really is just acting as our solvent for the reaction mixture. And then what we're going to do is we're going to transfer the nitrosonium ion that we've just created in our first flask down to our second flask. So let's go ahead and draw in that nitrosonium ion as a reagent, and I'm going to flip it on its side a little bit. And this will be the active electrophile for this reaction. But before we go any further, we need to look at this substituent that we have here and determine whether or not it's going to favor ortho and para regiochemistry or if it will favor meta regiochemistry. In this case, we can see that it's an electron withdrawing group, and most electron withdrawing groups tend to favor meta substitution. So what that means is we're going to favor reactivity at one of these sites that would be meta relative to this substituent. All right, does it matter which one? Not exactly. It's completely symmetric, which means either one, regardless of which side it reacts, will give you the exact same product. All right, so let's show this reaction. In this next step, this aromatic ring will attack the nitrogen in the nitrosonium ion and kick electrons up to the oxygen. And we'll get a new nitro group installed. We still have a hydrogen coming off there, and we would have a positive charge right next door. This is called a sigma complex, or a rhenium ion. This sigma complex is quite unstable because, as you can see, we've lost aromaticity in the system. This carbon right here is sp3 hybridized, which isn't very good. All right, so now what we need to do is we need to reform aromaticity. So we need some sort of weak base to help restore aromaticity. And in this case, the best base that we have around is actually the water that was kicked off in step 1. So the water that was kicked off in our first Erlenmeyer flask can grab this proton, can clamp down, and it can restore aromaticity to the system, giving us a final product that has a nitro group, which I'll just abbreviate as NO2, and complete aromaticity. If we think about what the name of this compound would be, this would be methyl meta nitro benzoate. And there we go. When we're done with this reaction, what we may have to do is purify it a bit more because we may get a small amount of ortho or para-substituted product, but that's easily performed using recrystallization with methanol. So we'll see if that needs to be done.
All right, in my first ice bath, what I have is a small 125 milliliter Erlenmeyer flask. And I placed that flask in an ice bath to keep it nice and cool. And what I've done is I've measured out 4.1 milliliters of nitric acid, and I've put that into that small Erlenmeyer flask. I tried to keep it nice and cool because in the next step, what I'm going to do is measure out 6.1 milliliters of concentrated sulfuric acid, and I'll add that in slowly. If you remember from the reaction mechanism, the sulfuric acid will actually protonate the nitric acid, and that reaction is quite exothermic. So we need to keep the temperature low to keep it from getting too hot. All right, so we'll keep on adding that the sulfuric acid to the nitric acid. And if you recall from the aromatic substitution chapter, what we're going to create in this flask is the nitrosonium ion. Once we have the nitrosonium ion ready, we can transfer that to our aromatic reagent and get the nitration reaction to occur. But it's essential that our reagents are kept cold during this entire reaction. All right, in my second 500 milliliter Erlenmeyer flask, what I've done is I've added about 15 milliliters of concentrated sulfuric acid, and then I've also slowly added my starting material to that sulfuric acid under ice bath conditions. Furthermore, what I've done is I've actually added some sodium chloride to the ice to drop the temperature even lower. So in this Erlenmeyer flask, what I have is my nitric acid and sulfuric acid. This creates my nitrosonium ion. And then over here, I've got my starting material and my sulfuric acid. The sulfuric acid in this flask with my starting material is acting as a solvent. And once this drops below 5 degrees Celsius, my plan is to move the nitrating mixture from this flask all the way over to that flask slowly, because I don't want the temperature in this flask to jump above 5 degrees Celsius. All right, so I've let everything cool down for a while. The temperature of my starting material in sulfuric acid is below 0 degrees Celsius, and my nitrating mixture has been sitting in the ice bath for a while. So what I'm gonna do is I'm gonna set up a time-lapse video, and I'm gonna transfer over the nitrating mixture from this Erlenmeyer flask into the starting material really slowly. My goal is to keep the temperature in there below 5 degrees Celsius. Alright, as you can see, that was super fun. It took a while. You have to be really patient to keep the temperature down below 5 degrees Celsius. But now that I've added all of my nitrating mixture, I'm going to let this sit for another 5 to 10 minutes, and then I'm going to dump some ice water into the reaction flask in order to precipitate out my product. Okay, so I've had it sitting in my Erlenmeyer flask under ice bath conditions for about 5-10 minutes. And then in the second beaker, what I have is a handful of ice and some water up to about 250 milliliters. And I even threw in a stir bar. So what I'm going to do is I'm just going to turn on the stir. I've found that if you stir this while adding your starting material, it works a lot better. So let's get this stirring. And then I'm going to transfer the contents of this flask into there. There we go. Then I'm going to rinse this with a little bit of water to help ensure complete transfer. Oh, alright, while I'm waiting for my reaction to cool, what I'm going to do is get a beaker. I'm going to label it with my name and the product, and I'm going to get a piece of filter paper, and I'm going to record the mass of this. So the idea behind this is when I pull my filter paper off, put it into the beaker and let it air dry overnight, I can just subtract out the mass of the beaker, the label tape, and the filter paper to find the mass of my final product. Alright, so the mass of my beaker, label tape, and filter paper is 112.921 grams. Alright, so the ice has completely melted. I've been stirring it for a while. I can see some white precipitate forming. I've got my Buchner funnel set up. I'm going to turn on my vacuum. I've got my filter paper that I used to pre-weigh inside my Buchner funnel, and I'm going to pre-wet it with filter paper to ensure a nice tight seal. You hear that hissing noise. And then I'm just going to take this and I'm going to transfer all of my liquid in my Buchner funnel. Alright, I need to be careful not to overfill this, but I'm just going to give it a quick rinse. To ensure that I get all of my product out. Alright. I'm going to turn off my vacuum. And I'm going to dump my waste, and then I'll try to get a little bit more out. Okay, so I've been letting things air dry for quite a while, just to ensure that all that moisture is pulled off of the powder. And now what I want to do is I want to transfer the filter paper to my beaker and let it air dry in my drawer for a couple of days. Alright, so I let my product air dry for at least 2 days, and I've put it back on the scale and pulled out the stir bar. And it looks like the new mass is 120.375 grams. Alright, so let's calculate our percent yield, get an IR, an NMR, and a melting point range. Alright, so I took the melting point, and the melting point range was quite broad and quite low. So what I did was I moved my powder into an Erlenmeyer flask, and I've added about 10 milliliters of methanol to this Erlenmeyer flask. And what I'm going to do is I'm going to boil this solution, try to supersaturate my methanol, and then slowly let it crystallize out of solution. Hopefully this will give me a pure product that will have a melting point range closer to what we would anticipate for the product. Okay, so I've added enough methanol to my crude product where the crude product has dissolved completely while boiling. And now what I want to do is I want to cool this to room temperature slowly. And then once it's cooled to room temperature, I'll put it in an ice bath to encourage crystal growth.
Alright, for my next step, what I did was I put my cold solution into an ice bath, let the crystals form for another 10-15 minutes, and then I vacuum filtered my crystals and let air pull through my filter paper for a few more minutes to ensure that the crystals were completely dry. Now if I go ahead and I look at my crystals, you can tell that they're nice, sparkly, crystalline, and white. Alright, so now this looks much better than the clumpy precipitate that I had before. We can go ahead and get the melting point, we can get the IR, and we can get the NMR.